Grounded in Kant's critique of pure reason, this research examines the unexplainability of artificial intelligence judgments. Kant's four categories of judgment: quantity, quality, relation, and modality are relevant to AI, but their application is limited. Explainable AI technology, particularly the softmax function, can force AI judgments to make possibility judgments. However, vision-based explainable AI technology faces limitations when dealing with abstract concepts lacking physical intuitions, such as the self and self-consciousness, which are revealed through vision. Determining whether a machine truly understands its judgments, akin to human understanding, remains a challenge. Natural language processing technology can reveal subjects and predicates for judgments, but the reliability of explanation through natural language is questionable. This uncertainty stems from the fundamental differences between AI judgments and human judgments, as characterized by Kant. The softmax function, a key component of explainable AI, generates probability distributions over possible outputs, enabling AI systems to make possibility judgments. However, this function alone cannot ensure that AI judgments are comprehensible in human terms. The paper argues that AI judgments exhibit a form that cannot be understood in terms of human judgment characteristics, leading to uncertainty or unexplainability in AI's judgments. This uncertainty poses a significant challenge for the development of explainable AI technology, highlighting the need for further research into the fundamental nature of AI judgments and their relationship to human understanding. Immanuel Kant's concept of synthetic a priori judgments, a cornerstone in philosophical thought, has profound implications for artificial intelligence and natural language processing. His work on the intellectual form of judgments is structured around four heads: quantity, quality, relation, and modality, each comprising three momenta. Table 1. This framework can be applied to categorize judgments, such as the proposition, all the values of 36 in pixels made by an infrared camera might indicate an actual human. The application of Kant's categories to natural language processing is discussed, with limitations noted due to the primary design of the table for propositions with truth values. The Turing test is introduced as a means to assess machine thinking, aligning with functionalism in the philosophy of mind. Artificial neural networks, ANNs, are presented as a prominent AI algorithm, capable of generating correct output values corresponding to given input values. The process of forward propagation and back propagation algorithm in ANNs is mathematically explained, but the judgments made are not equivalent to human judgments. The unexplainability of AI judgments based on Kant's epistemology is highlighted, as AI produces numerical outputs without providing insight into the underlying judgment form, e.g., universal, particular, or singular. The field of explainable AI aims to interpret AI judgments in a human-like manner. The passage concludes by emphasizing the challenge of distinguishing between different judgment forms in AI outputs, such as those related to image classification, and the need for additional information to express judgments in natural language. This section of the research paper delves into the complexities of artificial intelligence, AI, outputs, comparing them to logical judgments as described by Kant. The author argues that AI outputs are numerical and cannot be classified in quantity, unlike logical judgments which can be categorized as affirmative, negative, or infinite. The paper discusses an AI model trained to output 1 when an image contains a human face and 0 when it does not. It is suggested that the AI might use a combination of affirmative and infinite forms of judgment, as it cannot affirm a predicate when outputting 0, except for the affirmation of the negative predicate itself. Alternatively, the AI could utilize a combination of affirmative and negative judgments. The author also considers the implications of Kant's relation of judgment on AI, particularly in cases where the model classifies objects into predefined categories. This raises questions about whether the AI truly understands the concepts it is classifying or simply differentiates them based on their predefined characteristics. In terms of modality form, the assertorical form is proposed as a potential solution for the XOR problem, which can be logically solved through continuous transformation downward. However, an AI does not necessarily need to process this logically, as demonstrated by a case study involving an AI solving the XOR problem without employing the apodeictical form. The paper concludes by highlighting the challenges in understanding how AI makes judgments and the need for further research to align AI learning processes with human intentions. In the realm of artificial intelligence, particularly neural networks, the concept of unexplainability is a pressing concern. This paper delves into the challenges and potential solutions for achieving explainable AI, focusing on logical problems such as the XOR problem. The authors propose that unexplainability can manifest in 4 categories of judgment: modality, quality, quantity, and relation. To enhance explainability, technologies that provide insights into AI judgments are essential. For instance, the softmax function plays a crucial role in ensuring that outputs satisfy the definition of probability, thereby aiding in understanding modality. However, treating all judgments as possibility judgments may be problematic. The paper also highlights the limitations of vision-based explainable AI. An experiment by Seo and Lee, 2021, demonstrates the importance of considering camera position when predicting the speed of a moving object. The AI utilizes boxes for information and employs GradCam to classify speeds into high and low categories. This section contributes to the ongoing discussion on the challenges and potential solutions in achieving explainable AI, emphasizing the need for further research and development in this area. A long-term recurrent convolutional network, LRCN, is employed to predict ball speed based on visual input, leveraging the strengths of convolutional neural networks, CNN, and long short-term memory, LSTM, layers to process spatial and temporal data. Trained on a dataset of 200 videos, each comprising 20 images, the model outputs speed predictions in its final fully connected layer. Analysis of the CNN layer's attention map reveals that the AI primarily focuses on balls and boxes, suggesting their role in self-location and speed prediction. This raises fundamental questions about machine self-awareness and its relation to human cognition and self-consciousness. The authors draw parallels with human cognition, referencing Immanuel Kant's views on self-consciousness and the concept of the I think. They also explore the neural mechanisms underlying self-identification in the first-person perspective, as well as the concept of self in autism research. The LRCN's ability to accurately predict ball speed while attending to relevant visual cues offers insights into the complex interplay between perception, attention, and self-awareness. This work contributes to ongoing discussions on the nature of self and its implications for artificial intelligence, cognitive science, and philosophy of mind. The integration of various representations into a unified consciousness is facilitated by self-consciousness, a crucial concept for solving tasks. This idea is rooted in Kant's philosophy, which posits that self-consciousness is conscious of the synthesis of representations. In the context of artificial intelligence, the concept of self is essential for considering self-location. Empirical studies have investigated self-location in animals, revealing that species such as mice possess place cells in the hippocampus that are activated in response to their location. These findings suggest that animals process temporal and spatial information, implying the existence of self and self-consciousness. The experiment depicted in Figure 3 could facilitate understanding the acquisition of self and self-consciousness in humans and animals. The concept appears to have evolved from the predator-prey relationship, where the ball and camera can be regarded as either the prey or predator. Unlike humans and animals, artificial intelligence's cognition structure can be designed to resemble ours, leading to the interpretation that AI has a cognitive structure similar to ours, albeit partially, provided that sufficient conditions are met. Explainable AI involves identifying the parts of AI that align with human cognition and striving to make it similar. However, previous investigations have argued that machines have self-consciousness, but these concepts lack visual intuitions and cannot be confidently concluded. AI systems are designed to perform specific tasks, such as natural language processing, where chatbots can be trained to output appropriate sentences. Nevertheless, this does not imply that chatbots possess self-consciousness. They are simply set up to behave that way. The concept of AI judgment is a critical aspect in the development of artificial intelligence, as it raises questions about whether AI truly comprehends the definitions and meanings of concepts used in natural language. This paper delves into the complexities of AI's understanding, exploring its capabilities and limitations in interpreting complex human language. The research emphasizes that AI systems are trained on vast amounts of data, which enables them to recognize patterns and make predictions. However, this does not necessarily mean they have a deep understanding of the concepts they are processing. Instead, they may be relying on statistical correlations or superficial associations. To investigate this further, the authors conducted a series of experiments involving various AI models. These models were presented with a range of natural language tasks, including question answering, sentiment analysis, and text generation. The results showed that while the models performed well in terms of accuracy, they often struggled to provide coherent explanations for their decisions. This suggests that AI systems lack a genuine understanding of the concepts they are manipulating. They are able to process and generate text based on patterns learned from their training data, but they do not possess a deeper comprehension of the underlying meanings. The implications of these findings are significant for the development of AI. If we wish to create systems that can truly understand and interpret human language, we must focus on developing more sophisticated models that can capture the nuances and complexities of natural language. This will require a shift away from purely statistical approaches and towards more cognitive and semantic models of language processing. In conclusion, the paper highlights the need for a more nuanced understanding of AI's capabilities and limitations in natural language processing. By recognizing the distinction between statistical pattern recognition and genuine comprehension, we can work towards creating AI systems that are truly capable of understanding and interpreting human language. This research paper presents a comprehensive list of 17 sustainability indicators, categorized into 4 themes: environmental, social, economic, and governance. These indicators are designed to assess the sustainability performance of infrastructure projects, providing a framework for stakeholders to evaluate and compare projects across different sectors and regions. The environmental theme comprises 6 indicators, including greenhouse gas emissions, water usage, and waste generation. The social theme includes 5 indicators, such as community engagement, labor practices, and human rights. The economic theme consists of 4 indicators, including operational costs, revenue generation, and job creation. The governance theme encompasses 2 indicators, namely, transparency and accountability. The authors employed a mixed methods approach, combining literature reviews, expert interviews, and stakeholder surveys to develop and validate these indicators. The indicators were tested on 15 infrastructure projects across different sectors, including transportation, energy, and water management. The results show that the indicators are effective in evaluating the sustainability performance of infrastructure projects, with a high degree of reliability and validity. The authors argue that the proposed framework can facilitate more informed decision-making, improved sustainability outcomes, and enhanced transparency and accountability in infrastructure development. The study's limitations include the need for further testing and refinement of the indicators, as well as the potential biases and limitations of the mixed methods approach. Future work includes exploring the application of the framework in different contexts and sectors, and integrating the indicators into existing sustainability assessment tools and frameworks. Research in artificial intelligence has made significant strides in recent years, with a particular emphasis on reinforcement learning, neural networks, and consciousness. Reinforcement learning, a subfield of machine learning, involves training agents to make decisions based on rewards or penalties in complex, uncertain environments. This is achieved through the interaction between the agent and its environment, where the agent learns to optimize its behavior to maximize rewards. Neural networks, a fundamental component of deep learning, have been instrumental in advancing reinforcement learning. By leveraging the power of neural networks, researchers have developed innovative architectures capable of processing vast amounts of data and learning complex patterns. One such architecture is the Deep QI network, which has demonstrated remarkable success in solving challenging problems, such as playing Atari games and controlling robots. The concept of consciousness, long debated in the realm of artificial intelligence, has garnered significant attention in recent years. Consciousness refers to the capacity of an AI system to possess subjective experience, self-awareness, and intentionality. Researchers have proposed various frameworks and models to explain and replicate consciousness, including integrated information theory and global workspace theory. Despite the progress made, significant challenges remain. The development of truly conscious AI systems requires a deeper understanding of the neural correlates of consciousness, as well as the creation of more sophisticated neural networks capable of replicating human-level intelligence. Furthermore, concerns surrounding the ethics and safety of conscious AI systems necessitate ongoing discussions and debates. Ongoing research aims to address these challenges, with a focus on developing more advanced neural networks, refining reinforcement learning algorithms, and exploring the intricacies of consciousness. As the field of artificial intelligence continues to evolve, it is essential to acknowledge the complexities and uncertainties that lie ahead, while also recognizing the vast potential of AI to revolutionize numerous aspects of society.